I have the graded homework here. This is homework 1. Okay. I was told to hand it out or hand them out in class to you. I can either put them here, collect them after class, or I can pass them around. Passing them around so that it's okay with you. If passing them around, you would lose your privacy. Okay, you don't sue us for it. Good question. Yes.
Are we having any like extra special like review sessions or anything for the test coming up?
I think they should be, yeah. The whole course director by his
There's
usually
one.
arrange for some review session.
Yeah, there's one review session, I think on Tuesday.
On Tuesday? Okay. Maybe you can find out the time and announce.
The announcement will go out on the website.
It's already
It's
on the
on the
website?
No, it will go out on the website.
It will go
Do
on
you
the
know when?
website. When the
Huh?
review
When
session.
the announcement's going out or just?
I don't know.
Okay, it's time to get started. Okay, are there any questions before we get started? I already got one just now. So, if you have any questions, please let me know. Okay, let's get started. Today we're going to talk about linear time invariant system. Or the short for this is LTI system. What are LTI systems or linear time invariant systems? So we have to learn the concept of linearity and then the concept of time invariant. So let's think about the concept of linearity. You have seen that concept in mathematics before. You call a straight line a linear line. For instance, if I was to plot x versus y, this is a straight line is a linear line. Okay. So in this case, y equal to ax. Okay, simple thing. And in a linear system, it is very similar to a linear line, the concept of a linear line. Say if you have y1 is equal to ax1, y2 is equal to ax2, then you will have the fact that k1 x1 plus k2 x2, if this is the input, if you can think of this as the input, and this is the output. This is the simplest of its kind. Okay, this is the input, and these are the outputs. So if we have x1 being the input with the output being y1, x2 being the input with y2 being the output, then the linear system says that if this is the input to the system, say we feed this into the system, then output should be given by this. Okay, if you plug this into this equation, the first equation, then you should get k1 ax1 plus k2 ax2. So it is just actually equal to k1 y1 plus k2 y2. So what it says is that you can denote this as being, if this has been the input, this would be the output. Okay, that's the definition of a linear system. But this concept can be generalized not to only a variable, but to a function of time, for instance. So if we have a system, and if this is my input, x of t, so this is not a very simple variable, but a function of time, and this means the output, y of t. So if we do two experiments, the first experiment, where I feed in a signal x1t. x1t could be a very different signal from x of t. These are functions of time. Okay, I will get an output, y1 of t. Okay, if I do this second experiment with the same system, if I feed in x2 of t, I get my output to be y2 of t. Okay, a linear system is defined to be one for which if I feed in k1 x1 t plus k2 x2 of t, okay, if I combine the input as a linear superposition of the previous two outputs, then the output is also a linear superposition of the previous output. So this is linear superposition, or you call it the principle of linear superposition for linear system. Okay, somebody asked me what the word superposition means. Because you see this word super all the time, right? Super loop, super node, superposition. Okay? I think the word super means big sometimes in English, right? Super node must be a big node. Super loop must be a big loop. But here I think the word comes from the word superpose. Superpose in English means putting one on top of another one. So it doesn't mean something super. It just means putting one thing on top of another one. So you can think about this word coming from the word superpose. Or superimpose, you see this word sometimes in use. Superpose and superimpose, or superpose just means putting one thing on top of another one. So this is the gist of the definition of a linear system. And if you want to test if a system is linear, you have to take that system to these tests. And if these tests are satisfied, then the system is linear. Okay? So we look at some of the systems where we have designed, like capacitors, inductors, resistors, and so on. And those are all linear systems for this reason, that the input and output satisfy all the tests that we put them through. This output is also sometimes called a response. Okay? And this is called the input most of the time. In some textbooks will call this output the response of the system. How that system responds when you put in a signal into that system. Okay? So we have looked at different kinds of linear systems. For instance, we have system where B, P, is L, di, dt. we can think of this as the input and this be the output of the response. And then we can have the other one, which is I of t is c dv t dt, where this would be my input and this would be my output. Okay? And this, of course, describes an inductor, and this describes my capacitor. We can also turn the input and output around by integrating this equation. So instead of calling my IT the input, I can also convert that into an output. So if I integrate this equation, I will get I of t is equal to an integration constant, actually, integration of 1 over L V of tau d tau. Okay, this is the general rule that we learned from calculus. Okay, of course you can write the integration constant in the most suggestive fashion and set the limits of integration so that this actually is the value of I at t0, and if I set the limit of integration to be t0 to t and put the 1 over L outside, then I have this equation over here. So this is now the output in this picture, and this is the input. Okay? And this is usually called a state. The state of the system before you have any input. Okay? The state of the system before you have any input. And output, as I said before, is also called a response. Okay? I can do the same thing to my other equation, the capacitor equation, and write it in terms of an integrator input and output system. And if I were to integrate this equation, I get V of t is equal to V of t naught. V of t naught is the value of V at t naught plus 1 over c integration of t naught to t d tau I of tau. Okay, I can also write the second equation in that manner. And this is my input now. This is my state. This is my output or the response. Okay, are there any questions so far? So I can convert these equations into integrator system so that it becomes an integrator instead of a differentiator. Okay, and we can test to see if these systems that we have designed this way are linear or not. Okay. So there are two kinds of response being outlined in the textbook. Okay, if you were to just say V of t is equal to V of t naught, setting I of t is equal to 0, this is called the zero input response. Okay, that is, if you were to set the system to have no input, the only output you get is the state of the system. This is called a zero input response. And if you do the otherwise, do it the other way around and set this term to 0, okay, and you have only the second term, where you set the state to be 0, this is called a zero state response. Okay, so you understand what the zero input response is and what the zero state response is. Does everybody understand these two concepts? Yes?
So what did you plug into the original equation to make all of the integral part drop?
I assume that there's no current going to this capacitor.
Okay. So I did it. Okay.
Okay, no current going to this capacitor. The only response that I get is state before I put in anything. So that was the only output I get. Okay, this is the zero input response. This is called a zero state response. So let's test to see if linearity is satisfied by this system that we have designed. And let's do example 3.9. In example 3.9, we have the system where you have an integrator. Okay, very much like what you have over there. The input is I of t. Okay, very much like this system over here. And then the output is v of t. And you can see that v of t is v of t0 as I have written over there. Plus, the textbook did not use 1 over c, okay? I just put 1 over c because I did not set c to be 1. Okay, the textbook just used c of being 1. And I want to test if this system is linear, okay, if it's zero state linear, zero state linear, is this zero state linear or zero input linear? Okay. So if this is a zero input system, if this is a zero state system, if it's zero state system, then the output is just related to the input via this equation over here. Okay? If it's really zero state, that means that it has no initial state. The state refers to the state of the system before you set or put in anything to the system. Then if I were to have I1 as my input, I will have V1 as my output or the response. And then if I were to put in a second, let me write this slightly further down. Okay, 1 over C P naught to T I2 tau d tau. Okay, so the first input is I1, the second input is I2. Now I want to combine the two inputs by using linear superposition. Okay, so if I were to have an input where I have a combined input of the previous two, then I will put K1 I1 tau here plus K2 I2 tau here. This would have been my input. Okay, what is my output in the third experiment? You can work out what V3 t should be by just writing out these two integrals separately. Okay, break it into two, and you find that V3 of t is actually equal to the first one. You take the K1 outside, it's K1 over C T0 T I1 tau d tau, okay, which is the first term over here, plus the second term, which is K2. If I were to take this K2 outside and take the C outside, it will be I2 tau d tau. So what is V3 expressed in terms of the previous outputs? If I were to use the previous output to write the right-hand side of V3.
K1 V1 plus K2.
Right, K1 V1 plus K2 V2. If you look at this, so the principle of linear superposition holds true in this test. So this is in fact a linear system. Okay? So bingo, we got the test. It goes very well. Are there any questions regarding this very simple test? Okay, let's look at the other one. The other one being the case when you have zero input. Okay, zero input, then the input and output relationship is just related by this. B of t is equal to B of t naught. Okay, that is a zero input response. This is zero input response. Okay, and then let me say that I just put a signal B1 t naught in the first time, and then I put a single signal, second signal, B1 t naught, the second time around, and it's quite clear that B3 t, if I linear superpose these two, is K1 B1 t naught plus K2 B2 t naught. It's just a linear superposition of the previous two responses. Okay, this is no-brainer. Okay, so this satisfies the linearity test. Bingo, it goes again. Okay. So quite straightforward. So are there any questions regarding this? Yes?
Were we trying to figure out if it was zero state or zero input, or is it both? I was confused at what we were trying to figure out.
Well, we are trying to figure out if it is zero state input. If it's zero state to begin with, okay, is the response linear? If it's zero input to begin with, is the response linear? In both cases, we found that they are linear. Okay, but this is not true if it's a linear superposition of both. Okay, linearity is only true if you have one of the two terms. Okay, it's very much like this line over here. If I reduce it back to one dimension to the simplest case, if I reduce it back to the simplest case you can imagine, this is still a straight line response, but it's not linear in what we have defined here. For instance, this curve can be defined as AX plus C, right? So if you have one input, AX1 plus C, you have the second input, AX2 plus C, and then if you have two inputs together, the input being now x3 being equal to k1 x1 plus k2 x2, this is our new input to this line, the simplest case we can imagine. Then y3 is equal to a, x3 plus c would be equal to k1 ax1 plus k2 ax2 plus c. And that, as you can see, is not equal to k1 ax1 plus k2, or it's not just equal to k1 y1 plus k2 y2. Okay? A straight line, a linear line with a constant offset, is not linear by our definition of a linear system. Okay, it has to be something that goes to the origin. Okay, so if you have two of them together, the system is not linear in our definition of linearity. It has to be either 0 for one or 0 for the other one. Okay. In mathematical parlance, this is also called a thin linear. It's not truly linear, but if you're interested in the mathematical term for it, it's called a thin linear. Okay? So let's do another example. Example 3.10. And here we have a differentiator. As we often see in the previous example, we have a VST, and then our output is just equal to minus RC dVs dt. Okay. Is this a linear system? We ask ourselves what the output is if there's no input to this system. This is a differentiator system. If there's no input to this system, the output is 0. Okay, so the 0 input response is equal to 0. Okay, which means that the state part is equal to 0. So if you look at this part of the system is equal to 0 because when there's no input, there's no output. So this part must be 0. So the state part must be 0. Okay, the state part is always 0. If something that always have a 0 output, if I just look at the state part, okay, the 0 input response, the state part only, it always have a 0 output irrespective of what you have for an input. It's a system linear. It is, right? It is, because it just represents this kind of line. It's a straight line that goes through the origin. Okay, so it must be a linear system also. So when it's 0 input, it is a linear system because there's no output. Then we look at the other one, which is the non-zero input response, which is this part over here. Okay, non-zero input response, and that clearly is linear. You can go through your test again. If the output linear with respect to the input. If I have V1S T be my input, then the output is minus RC dV1ST dt. Okay, V2ST is my input, then my output is given by this one, dt. And then it's quite clear that if this is my input, if the input is a linear superposition of the two previous input, then the output is just given by K1 minus RC. I'm not going to go through the algebra. I'm sure that you can go through the algebra and obtain it at this. Okay, you go through the algebra, you plug the left-hand side as the input, you get the right-hand side as the output. And it satisfies the principle of linear superposition. So the differential operator, a differentiator, is a linear system. Okay, an integrator is a linear system if you set the state input to be 0, the state part to be 0. Okay? Similarly, the differentiator is also a linear system. So, what happens if we have something like this that looks quite bizarre, that the 0 input response is something like this, as being given as one of the examples in the textbook. Okay, this is the 0 input response. That means that you set the input to be 0 so that the integral part goes to 0. So you only have the state part coming out. Is this a linear system? Definitely not, right? Because if you test it with y1, you test it with y2 as your input to the state. Okay, it's very clear that if you have y3 of t, where you linear superpose the two inputs k1 y1 plus k2 y2 square. Okay, you square that, this is not going to be equal to K1 Y. This should be T naught. Okay, to make things clearer, I should put this as T naught. T naught squared, and this is not equal to K1T plus K2 Y2T. Okay, so linearity is not satisfied. This, in fact, is not a function of time, so I shouldn't have write this as a function of time. These are just constants. Okay, these are actually constants. So if you look at this, this is not satisfied, and hence this does not satisfy the principle of linear superposition. And then the textbook gives another example of nonlinearity, saying that the total response of the system is such that it looks something like this. You have a system, and then you have an input as f of t. And then what comes out looks like a constant that is independent of time plus f squared of t. Okay? You can easily test this, that if you have f1 as my input, and then if I have f2t as my output or input, then my output is y of t naught plus f2 squared of t. And clearly, you can see that if I have f3, okay, if I have third system where I have k1 f1t plus k2 f2t as my input into this system, okay, this is my f3 kind of, okay, the third input, which is a linear superposition of the previous two input. It is not going to be equal to, this will be k1, this is my input now, k1 f1 plus k2 f2 squared is not going to be equal to is not going to be equal to the linear superposition of the two previous outputs. Okay, I'm not going to write it down. Okay, you can expand this and clearly see that has been true. So are there any questions regarding linearity? Linearity is like a straight line going through the origin. Okay, if a system has that property, then the system is linear. Okay, you just go through this very simple test of linearity. So now that you know everything about linearity, we can move on to talk about time invariant. What is the meaning of time invariant? Okay. Time invariant system means that if I have a system, okay, let me see what notation I use. Say if I have an input, f of t, I put into this system, and the output I get from this system is y of t. Or it could be the response. Okay, I use the word output and response interchangeably. Sometimes some textbooks will say response, sometimes some textbook will say output. Okay, this system is time invariant. Time invariant means that if I come back later, say this is my amplifier or my cell phone or some of those things that I have. Okay, if I use this system at a later time and perform the same experiment, my output is just going to be time delay. So the way to say mathematically is that if this system been the same, if I were to input something later with a certain time delay, okay, this is a time delay function, and then the output is just going to be time delay. That is just the meaning of a time invariant system. So you know this means a time delay, right? So if you have a function f of t, and f as a function of t, it might look something like this, or it might even look something like this. Okay, t1, t2, t3, and then if I were to plot f of t minus t naught, okay? So at t equal t naught corresponds to this case when t is equal to 0, so you will have t naught starting out here, and then you will have the function looking something like this. This other point here will be t naught plus t1. This other point here will be t naught plus t2. And this other point here will be t naught plus t3. So this is just time delay. So if a time delay a signal, an input signal, the output is just going to be time delay. That's what it means. It means that the system has not changed over this time period when you let it rest there. So if we have a time varying system, it would be bizarre, right? So if you have an amplifier that works differently a minute later, you wouldn't want to amplify it. If a cell phone that works today but doesn't work tomorrow, you want to throw it away. Okay? You want a system to be time invariant. And then if you combine the two, if the system has a property of linearity, and also having the problem of time invariance, then you call it a linear time invariant system, LTI. Okay. Why do we study LTI? The primary reason is just they're very simple to analyze. If something changes